Hello everyone, I'm Amanda and I'm very happy to be here today to present to you on my research topic of a statistical physical framework for uncertainty quantification of material parameters. I am from the National University of Singapore and my advisor is Professor Yan Wen Tao. So without further ado, let me begin. In my work, we focus on the laser powder bed fusion process, which is a very popular process for manufacturing products with complex geometries such as turbine blades, fuel nozzles, and this process offers significant advantages over traditional processes. However, a major bottleneck in this process is the quality inconsistency of the produced metal products, and as such, the objectives of my work today is firstly to analyze what are the main and interaction effects of the important input parameters that affect our output, and to actually quantify how uncertainty propagates from our input variables to our output quantity of interest, and also how the relationships of our inputs and outputs are related to each other, and finally to interpret the findings of our sensitivity analysis as well as our uncertainty propagation to provide practical insights for industrial 3D printing applications, not only for the simulation community, but also for the experimental communities. So I would like to present forth my statistical physical framework, which has the advantages of low computational costs, complexity, and is also a very simple implementation that is general enough for the majority of the community in additive manufacturing to understand, and hence is of practical use to them. So this is an overview of the framework covering the design of experiments, high fidelity thermofluid CFD simulations, and variable screening processes using both the statistical techniques such as ANOVA, half normal plots, and also validated by physics-based domain knowledge of the laser powder bed fusion process itself. And upon jointly validating the parameters from both statistical and physical perspectives, we then go on to construct multiple linear regression models that can serve as the purposes of doing a sensitivity analysis and uncertainty propagation respectively, in order to get results that can guide both the simulations and experiments. So first, I will start off with talking about the full factorial design of experiments as well as the thermal fluid simulations that we have conducted in order to generate our data set. So in our design, we have considered 5 material factors that are chosen because there has been limited studies on actually these highly sensitive material parameters in literature, but there has been majority of the studies have focused on process parameters instead, like laser power and scan speed. So in our study, we would like to actually investigate how these material parameters may also affect our output. And we have actually chosen to do a 2K full factorial for these 5 material parameters, because the full factorial not only allows us to study main effects but also potential interaction effects that could have significant impacts onto our response, which is chosen as the melt pool depth. This is because the melt pool depth is an important indicator of quality, as it could affect the resultant microstructure, and it affects finally it also affects the final quality of the output product, and therefore our output quantity of interest is the melt pool depth. And so the nominal values and standard deviations of our 5 material parameters have been determined based on prior domain knowledge as well as literature research, and this yields their upper and lower levels as such, as well as their corresponding standard deviations as shown in the table. And a 2K full factorial for these 5 material factors amounts to 32 CFD simulations that were performed on our thermal fluid model. So this is a typical result of our simulation, whereby on top we have an isometric view with the temperature scale showing the block, and below we have a vertical cross-sectional view of the melt pool. And so we can see the melt pool depth is marked out by D in the figure. And so by utilizing our simulation model, we have generated 32 sets of 32 data points, and by which we then moved on to the analysis part to perform variable screening from our data to identify the most crucial variables. So first I talk about ANOVA. So the null hypothesis was defined as the factor having no significant influence on the melt pool depth. And the alternative hypothesis is that the factor does have a significant effect on the melt pool depth. And how we test this is by using an F-test. So if the F statistic calculated falls within the rejection region, whereby we have used a significance level of 0.1, we would then reject the null hypothesis and conclude that the factor is significant. So we have actually considered 5 different model types, right? Whereby the first model only considers the main effects, which is the 5 input factors of interest. And the next model considers the main effects together with the 2-factor interactions, and so on and so forth until the final model, which is the full model. So this model consists of the 5 main effects as well as all possible interaction terms up to the 5th order interaction between the 5 factors. And these are the results that were found from the 5 different models, because we know that essentially ANOVA is a multiple linear regression model, so we can choose what terms we want to add into the model. So from the first and second model, we see that in a model that consists of either the 5 terms, the 5 input parameters, or the 5 input parameters and the 2-factor interactions, only 3 factors are actually found to be statistically significant based on the p-values, which is the laser power absorption, thermal conductivity, and viscosity. And we see that as we incorporate higher order interactions like 3rd and 4th factor, the only significant factor now is the laser power absorption. And as we reach the full model, we realize that we do not get any applicable results. So the reason for this is because in the full model, there is actually a lack of random fluctuations in these deterministic simulations that causes our results to not be applicable if we consider the full model, because there is no terms that can constitute to the noise. And I shall not go too much into detail about this, but I will talk more about how we have tried to use further analysis tools to complement our ANOVA analysis. So next part, I will talk about how we have used half-normal plots and domain knowledge to validate our ANOVA findings. So this is a half-normal probability plot of all the effects. Since we were not able to get useful results from our ANOVA model, we have used a half-normal probability plot instead. So how to interpret this plot is that points that lie near the line are actually identified to be not significant, but obvious outliers are actually identified or suspected to have a very significant influence on the response. And so here in the plot, each point represents an effect. It could be a main effect or an interaction effect. And from the plot, the only obvious outlier, as we can see, is A, which represents the laser power absorption. And for the rest, it lies pretty near the line, so it is subjective and we want to have further analysis. So now we try to exclude this variable A, laser power absorption, and see what kind of results that we have. So when we exclude laser power absorption, right, we essentially are only considering the other 4 variables. So we have 16 data points that we are interested in looking at. And even though we have excluded the laser power absorption, we know that these 16 points actually correspond to when the laser power absorption was at the high setting, right? And we see that from this plot, the most significant variable is identified to be B, which is the thermal conductivity, and the rest, since similarly they are near the line, they are subjective, right? So, and now we see for the next 16 values, right, corresponding to when the laser power absorption was at the low setting, the most significant variables are the main effect of the viscosity, as well as 3 interaction effects that lie far from the line, right? The interaction between thermal conductivity and the surface tension coefficient, right, as well as the other 2 interaction effects. And so this is the inference that we can draw from the half-normal plots, which excludes the laser power absorption. So we notice that when the laser power absorption varied from the low to high level, this affected the factors that were found to be significant. So what this implies is that changes in the levels for the laser power absorption will actually affect the response of other factors such as thermal conductivity and viscosity, which means that the interaction terms could be potentially significant, right, between the laser power absorption, thermal conductivity, and the laser power absorption, as well as the viscosity. And so this is a summary of what we have concluded from the half-normal plots, that these are the corresponding main as well as interaction effects that are suspected to be significant. And what we want to do is to actually verify this with physics-based domain knowledge. So now we move to the next segment of the statistical-physical framework, which is on physics-based evaluation. So from domain knowledge, we know that these are certain important dimensionless as well as some dimensional parameters that are very closely related to some very important physical phenomena of the laser powder bed fusion process, such as the Marangoni Convection, heat transfer, as well as even material effects. And the reason why we have selected some of these parameters are because they also contained the input parameters of interest in our study, and therefore they allow us to actually study what researchers have actually reported about the key input parameters of interest in our study. And so this is some of the observations from literature. For example, looking at the Pratt number, which consists of 2 variables of interest in our study, the viscosity and the thermal conductivity. So it has been found that high Pratt numbers cause wider and shallower melt pools. So what this implies is that this has a significant influence on the depth, because we see that a change in the Pratt number causes such a huge change in the melt pool shape. So this means that our response in variable of interest, the depth, is indeed affected by the Pratt number. And since Cp, which represents specific heat, is a constant, we know that any variability of the Pratt number comes from the input variables of interest, either the thermal conductivity or the viscosity. And therefore we conclude that either the main effect of the thermal conductivity or the main effect of the viscosity and all their interaction term are significant, and that is what produced such a significant influence on the melt pool depth when one of these variables were actually changed. Yeah, and so this is how we actually drew the inference, right, for the input variables of interest in that was reported in literature. And we repeat the same right now for the Marangoni number, and we see that a change in the Marangoni number actually caused a change from the response aspect ratio of to become from linear to nonlinear. And therefore, we conclude that these are the following significant terms that potentially have a significant effect onto our response variable of interest. And we repeat the same for the rest of the dimensionless parameters as well as dimensional parameters in the table. So this is a summary of the joint statistical-physical evaluation, whereby on top we have a summary of the terms found to be significant from physics, and below we have summary of the terms found to be significant from our statistical results, both from the ANOVA findings as well as the half-normal probability plots. So we see that there is a huge overlap, right, as marked out in red by the parameters that were commonly identified to be significant. And so this provides statistical physical validation, which is so important because not only we managed to show through statistical results that these are the variables that are significant, but it's also verified with the knowledge of the domain experts that say the same thing, that we have also found the same result. And we are able to then move on to the next part of the analysis, right, upon reaching this common ground, to construct multiple linear regression models based on the jointly validated parameters. So first, we used the 12 validated parameters, right, for this segment. And the first part focuses on uncertainty propagation, which is actually related to each other as defined by Citelli. So here, sigma d represents standard deviation of the melt pool depth, which is our response variable of interest. And the standard deviation is a representation of its uncertainty. And this is how it's related to the input uncertainties. And here, the partial derivatives are actually being estimated by multiple linear regression coefficients. So in order to estimate the values of these partial derivatives, we construct a multiple linear regression model M1 based on the 5 main effects of our input factors. And then we use the least squares regression to estimate these values and substitute them back into the defining relation to actually define the relationship between the output uncertainty of the melt pool depth as well as the 5 input uncertainties. And by doing so, we then manage to obtain results in terms of a graph of how the output uncertainty actually changes together with the input uncertainty. So here, we have normalized the input standard deviations to be within the range of 0 to 1. And x1 to x5 represents the laser power absorption to surface tension, temperature, sensitivity, respectively. And can be seen from the plot that the laser power absorption propagates the most uncertainty of 0.025 and is much higher than that of the rest of the 4 variables. And this is very consistent with what was found from ANOVA as well as our half-normal probability plots. And the practical guidance from this result is that we need to pay very careful attention to the laser power absorption in both simulations as well as experiments. So in experiments, we need to be very careful about accurately measuring this parameter, taking into account potential variations that can happen because of surface roughness, powder oxidation, and so on and so forth. And in simulations, we need to carefully derive the laser power absorption from fundamental physics, perhaps using a ray tracing model or calibrating against experiments, because our goal is to ensure the highest possible precision for the laser power absorption. And as we exclude the laser power absorption to study the effects of other factors, we see that the next highest uncertainty is 0.00011, which is an order of magnitude of 100 less than that of the laser power absorption. So we see the laser power absorption really does have a dominating influence. And this is the order of influence of the remaining 4 factors and some of the general suggestions regarding them. So since it's found that the surface tension temperature sensitivity is more important than the surface tension coefficient itself, perhaps we want to pay more attention to material compositions or impurities that alter the value of the surface tension's temperature sensitivity in experiments. And in simulations, perhaps when we're exploring the processing parameter ranges, we want to use ranges with similar thermal conductivity and viscosity after taking into account the laser power absorption, since these are found to be the next 2 most significant factors. And so right now, I would just go into the sensitivity analysis, which makes use of sigma normalized sensitivity indices as defined here to rank the parameters, 12 parameters based on their importance. And again, we define another multiple linear regression model, and we use the coefficients to estimate the partial derivatives. And we include a normalization factor in order to prevent the units from coming into play. And this is the result of the sensitivity analysis. So we see that again, the laser power absorption is the most important variable. And the order of importance of the top 6 parameters, right, which are most important are shown as follows. And the terms marked with star are actually also statistically significant. So we see that this is very consistent, right? The results of the sensitivity analysis and uncertainty propagation are matching and are furthermore consistent with the earlier on results we had from ANOVA as well as the half-normal probability plots. And an interesting finding here from the sensitivity analysis that we could not observe from the graphical plots is that the interaction effect of the thermal conductivity and the surface tension temperature sensitivity was even larger than the main effect of the surface tension coefficient itself. And this is also not surprising because we know that this term is very closely related to the Marangoni Convection, which has been found to have significant influences on the melt pool geometry in literature. And so I've come to the conclusion of my study, which is that these are the following 12 parameters that have been found to be significant, right? Not only from statistics, but from physics. And these are some consistent results we have gotten from the multiple analysis tools that we have used. So laser power absorption propagates the most uncertainty and is also the most sensitive variable that has dominating influence over the rest. And the interaction term between the thermal conductivity and surface tension temperature sensitivity is even more significant than the surface tension coefficient itself. So the practical guidance is to pay careful attention to laser power absorption in both simulations as well as experiments to ensure highest possible accuracy. And with that, I've come to an end of my presentation. Thank you very much for your attention.